Hello everyone. Today is the 34th day of Leetcode 75 challenge. Let's begin with the 34th question. Question 872. Leaf similar trees. The level of the problem is easy. I will request you to read the question beforehand as I will deep dive into the PPT and explain it in simpler way. Now let's understand the problem in the easiest way possible. So you are given the roots of two binary trees. Fine. You're given two binary trees. Fine. And the leaf in a binary tree is a node with no left or right child. So this is a leaf node. This one, and this one. Since it does not have any left or right child to it, that's why it's a leaf node. Fine. The leaf value sequence of a tree is the list of values of its leaf nodes collected from left to right. Our task is to determine whether the two given binary trees have the same leaf value sequence. Basically, they are trying to say that we have to compare the leaf value sequence of both the trees. Suppose it contains 1 and 2, and this also has 1 and 2 as a leaf node, and we check the sequence from left to right. Fine. For the sequence of the first tree comes out to be 1 and 2 for the leaf node, and for the second one comes out to be 1 and 2. Since they are similar, and we have to return whether they are same or not. So basically, we have to return true if both these trees leaves are similar, have the same leaf value sequence. Otherwise, return false. Fine. This is what the question is asking. Question is pretty simple and straightforward. Fine. Now let's look at the constraints. The number of nodes in each tree will be from range 1 to 200, and both of the trees will have value in the range of 0 to 200. Fine. Now let's move to the next slide. Let's understand the input output of the problem. Suppose if you could see here 6, 7, 4, 9, 8. These are the leaf nodes for the first tree. Fine. And the sequence from left to right comes out to be this. Fine. First tree 1. T1 is tree 1 and let it be T2 as tree 2. If you could see 6, 7, 4, 9, 8. Okay, these are the leaf nodes. It was 4, 6, 7, 4, 9, 8. Fine. And the output is true. Why? Because if you could see the sequence is from left to right is this 6, 7, 4, 9, 8. And for tree 2 also, if you could see the sequence from left to right is 6, 7, 4, 9, 8. Fine. So that's why both are equal. So that's why our output is true. Okay. It does not matter whether the depth of this particular leaf node is 10, 3 or 2. It just has to be the leaf node and sequence has to match. Fine. That's all. Fine. Let's move to the next slide. To understand what problem is asking, we should build up an intuition to the problem. Fine. Let's start by understanding the goal much more clearly. So we are given roots of two binary trees. Fine. So let this be the binary trees. Okay. And our goal is to determine whether the two trees have the same leaf values sequence. The list of leaf node values from left to right. Fine. Okay. So as you understood the question that if it is 1 and 2 and this is also 1 and 2, the leaf node sequence from left to right for this tree is 1 and 2 and for this also is 1 and 2, right? So what could be the brute approach or the brute force approach which would come to your mind, or the easiest one which would come to your mind is that we can traverse complete tree. Fine. But if you do that, there could be an issue. For example, if a tree is in this manner, let me draw another tree. So these are the two trees. If you try to traverse complete tree and store their values in array 1 and array 2, okay, and try to compare whether their leaf nodes are somewhat similar, it will not give you the correct answer every time because the structure of the trees might differ, right? And because of that, the array size will might differ, plus the sequence might also differ with it, right? Even though if the sequence for the leaf nodes are similar, if you try to compare them, it won't be giving you a correct answer. It will be a much more, you could say, unorganized way of traversing the tree and storing the answers and looking into it. It won't guarantee you a 100% correct answer every time. Fine. So not much more discussing about this brute force approach. Let's go to the one which might help us to resolve the solution or get into the solution. We could aim for a recursive solution that traverses each tree, collects its leaf values in order, and then compares the two resulting lists. Yeah, this could be done because in the previous one, what previous brute force, we were traversing every node and storing it in our list, right? And that was not 100% correct solution, right? But in this case, what we will do, we could just traverse the complete tree. If we encounter a leaf node, we could store it in our array somewhat array. Okay. And here also, if you encounter one you stored, then here it is another, right? So if we go in a sequence from, for example, left to right, we will of course get a proper sequence of leaf nodes from left to right. Okay, and this way, if we can fill up two arrays, and if we try to check whether both the values or the sequence are same or not, we could get the answer. Yeah, that makes some sense. Okay, so now let's try to visualize that process, how we gonna do it, right? So suppose we have a binary tree again, right? And the leaf nodes are 6749 for the tree one and 67449 for the tree two. Now both the trees have the same. Let me remove. Now both the trees have the same leaf sequence, so the output is true. Fine. Now suppose this is what it was. It was six, then it was seven, then it was four. Um, wait. Let me make here four and make this as nine, and I will clear this one. Okay. So this is tree one. Let's take another binary tree as similar. I will take the similar structure. Okay. Right now, I'm not thinking much more about it. Okay. So this is two binary trees. And to collect the leaf sequence, what we thought of a recursion function that traverses the tree and adds a node value to the list only if it's a leaf node. Fine. Only if it's a leaf node. Now, otherwise it won't be storing, right? And once both the trees are traversed, you simply compare the leaf to leaf of the lists, right? So what we are trying to do here, we will be traversing the complete binary tree. Got it? If we reach at a leaf node, and we have some condition to check for it. And if it is a leaf node, we will just put it in the no the list. And once it is done here, it will go back and then come to this side, right? Then it will automatically have the sequence from left to right. Fine. So this way we could get the both of their lists and we can compare them. And now let's try to understand how we can simulate this. Now we have the idea, okay, what we are going to do, but how are we going to simulate it, right? So let's take that part. Okay, now let's try to look at it. So just don't look at this part right now. We will just try to just define a helper function to check for the the particular things. So when we are traversing, if we come after we are iterating from left, okay, root left, left, then we encountered here, right? Now how we will figure out that whether it is a leaf node or not? What is the definition of a leaf node? A leaf node does not have left and right nodes. Fine. So we will come here in the node, in each node basically, we will check if the node dot left is null, fine, and node dot right is also null, fine. If this condition comes out to be true, this means we are standing at the leaf node, right? And as soon as we got to know this, we will just put it in our list, and after that we'll go back and we'll come to the next node or the right node or the right root. Fine. And we'll check for the same condition. We got 7. We'll put it. Again, we go back to the root node. And from here, we go to the right. Then, since we have the left, we'll go to the left and we will put 4. Similarly, we'll come back and go to the ninth part and we will put 5 here, right? So, this way, we will get the complete list for both of the trees. Fine. That is the same thing I have written here. If the current node is none, we'll do nothing because this is a base case. Because if the node does not exist, we cannot do anything, right? And we recursively call the leaf function on the left and right children of the current node. And this ensures we gather all the leaf values from left to right order. Finally, this is the main function which is given. We return the or we will have the compared completely to list and return it here. Now keep in mind one more thing that you could have a thought that why we are going from left to right traversal, why not right to left? Because when you write, suppose this is a function, you write here root left. Then here you write function root right. So when until and unless the left condition is not falsified or we have not got a base case where it says that that root is null, fine. Whatever base case you provide, in this case we have the leaf node as a base case. So it will keep on going to the left. Fine. When it encounters the base case and all the calculation is done, it goes to the right. It checks, okay, nothing is there. Then it goes back. Then this node has already traversed the left part, right? This function has already been called for this particular node, right? So this function, now the function for the right call is left for this particular node. So we will traverse to the right side then. Okay. Similarly, when we come back, we check, okay, for this node, the left traversal is done. Basically, this function has been called. Then now we have to do for the right one, right? When we come here, we check. The recursion automatically does this task basically. When it comes to this node, it checks, okay, we have the left now, okay? Then it goes to the left, left, and left. Then it checks that, okay, left is done. Then we have to check for right. Then when both of them are done, we go back. Okay. If you have confusion or no, if you have confusion about this recursive part, how tree recursion or tree traversal is done, I will request you to please have a brief knowledge about it, how traversal is done. And if you are new to recursion topics, I will request you to go and read about recursion and then come back to the solution or the intuition of this particular problem and try to solve it. Then it will be much more easier to you to get familiar with the problem. Fine. So from here, what we figured out? We figured out we use recursive depth first search here. Why depth first search? Because we are going into the depth. Fine. If it has been written as breadth first search, it means that we are going breadth wise or level wise. Fine. So we ensure only leaf nodes are stored and that are collected in the left to right order. Okay. And comparing the results of the given list. Basically, when we reach to the leaf node, we store it into the list, right? So we compared them and we did the answer. Fine. So this is the thing what we figure out. After following these three steps, we could solve our complete problem. Now let's move to the next slide. Now, since we got the intuition of the problem, let's look into the approach, how we're going to solve it. Fine. This is the step one. Define a helper function to collect leaf nodes. Okay. Okay, let me make one more thing clear to you. Since in Leetcode, we have been given two functions, right? One is the main function given by Leetcode, and another is the helper function, which I have created, which will be called within the given main function. Fine. This will be much more clear when we will look into the code. Fine. For example, let me make it clear itself here. Leaf similar is a function given by the Leetcode. Fine. Within this function, I have called helper function, which is named as leaf. Fine. That's the thing. Okay. Now let's come back here. We create a recursive helper function leaf which takes a list and a root, okay, that collects the leaf node values from the tree. If the root is none, we return immediately because supposed if you don't have, suppose this is a tree, and if you check, okay, we don't have any node here, we return, right? If we don't have any node, we return, fine. And also, if you don't have the tree itself, okay, the given tree is null, then also we return. If the current node has no left or right child, it's a leaf. As we saw the conditions before that, if left is null and right is also null. So we just return the thing. Fine. That it's a leaf node, so store it into the list and go back. So recursively we call for vroot left to process the left subtree until and unless we hit the base case condition, which is this one. And after that we go to the right subtree and we do the thing. Fine. Why we have to do this? Because we need to gather the values of all the leaf nodes from left to right order. The recursion naturally traverses the tree in pre-order fashion. Fine. Now after doing that, collect the lift sequence from both trees. Now wait. Suppose we are given tree 1 and tree 2. Fine. So for the leaf function which we created, it will run for v1 or the list 1 and tree 1. Fine. Again, we'll call the leaf function with v2 or the list 2 and tree 2. Why we are doing this? We are doing this because we have to separately collect the leaf sequences for both the trees so we can compare them. If we send both the trees together and both the list together in one call, it will be a jumbled kind of a thing, and the categorization of the nodes or leaf nodes won't be much clearer, right? That's why we call it differently. It is also an optimized part to do it, and that's why we do it, and that's the thing. Now in step 3, after the function has been called for both the trees, we have the list filled with values, right? We just compare them, whether v1 is equals to v2 or not. If it is equal, we could see return true if both lists are equal. Otherwise, we will return false because lists of similar trees must have identical leaf sequence in same order, so the direct comparison is sufficient. That's why we do that and we return it, right? I hope you understood the approach. Now let's move to the next slide. Now, the code is the exact copy of the approach we discussed earlier. Let's understand it line by line. Okay, let's begin with declaration of list, which will store the sequence of the leaf nodes. Fine, this is what v1 and v2. Now we call this function leaf two times, one for the root 1 and another time for the root 2, so that you could traverse both the trees differently and store the sequence in a better way. Fine. And if you look at the function more clearly, if the root is null, we return. Fine. Otherwise, if root left is also null and root right is also null for a particular value, we just put it into the given list and we call for the left part. And if left becomes false some times later, we call for the right part. Fine. This is how we traverse in a tree. This is the basic structure of traversing in a tree, that is nothing much complex until other than this condition of checking for the leaf node. And after that, we just compare whether the values which we are stored in both the v1 and v2 are similar or not. If they are similar, we return the values. And this basically returns true or false if both are same, right? Now the complete time complexity comes out to be O of n. And let me break it down. It is basically O of n for the tree 1 plus O of n for the tree 2, which sums up to be O of 2n, and which is basically equals to O of n itself. Fine. And the space complexity is also O of n. O of n reason being O of n, it's not basically n because we are just putting into the leaf nodes, right? And leaf nodes is not equal to the complete tree. And plus O of n for the two of the lists, which sums up to be O of 2n, and which is basically O of n at the end. Fine. So that is the thing. This is the time and space complexity for it. I hope you understood the code explanation. Now let's move to the next slide. Now, since we have the understanding of the code, let's look at the dry run of the example. Fine. Uh, Let me draw the tree itself here again. Okay. Now I have drawn the trees here, tree 1 and tree 2. Great. Okay. So I have brought down the code here basically to make it much more easier for you to understand. Okay. So let me write here v1. Let me write here v2. Fine. Okay. So first we iterate or call the function with tree 1 with v1 and root 2. Fine. So if we start from here, if we check if root is null, no, it is not null. Okay. So then we check if the root left and right are null. No, it is not. So what we call? We call the root left function again. So we come here. Now this is the root value. Fine. Again, we check for the same condition if root is null or left right is null. Now, no, right? Then we call the left part again. So we come here. Now we're standing here. Now we check if the root is null. No. But its left and right are null. Yes, it is. So what we do? We append the value and we check if root left is null. Again, it is run, right? So we return. We go back. Then we check, then if it is returned, then we are in this function call of the root right. We check here. If it is null, yes, it is null, right? So again it returns. Fine. Both functions calls are done. Now we are standing in this node again. Now for this node, the left call was done already, if you remember. So we will go for the right node, right call. So we come here, we check for these following conditions. They are false. Okay. Then we call the left part again. We come here. Then we check for this condition becomes false, but the root left and root right is false, right? It's null here basically. So we store 7. Then we check for the root left, it is null. So we return root 9, right? That then also it is null, right? So we return it. Okay. Now for this part, the left call is already done, right? So we go for the right call. We come to the this node. We check left is null, right is null. Yes. So we store it here and we check for, we call the root left function again. It is null. So we return root right call here. It is null. So we return it again, right? So the call for this particular tree is done, right? We just clear this once. The complete call for this particular subtree is done. Fine. Now from here, if you remember, we started from here. We started with the left part call, right? Now the left call for this particular node is done. So we go for the right call. Okay. So we come here. For this node, we check if left and right is null. No. Then we call the root left part. Then we come here. Then we check left is null, right is null. Yes, this condition becomes true again. So we store 9. Then we go back. Then we check for the left node is null. Then we return. Then we go to the right call function. It is null again. So we return back. Fine. Now for this node, The left function call is already done, right? Now we'll come to the right call. Here again we will check if left and right are null. Yes, it is null. So we store it and we check if the root, then we call the root left part, right? It is null, so we return. Then from here we check the right part, it is null, so we return. Fine. So right and left call for this node is done, so we return that. Left and right call for this node is also done, so we return it. Fine. So at the end, for this we get v1. Okay. Similarly, for this tree also, tree 2 also, we get 6, 7, 4, 9, 8 in the similar fashion. Okay. And these two calls are done. Then after that, we check whether values of both the list are same or not, right? Since it is same, we return true. Fine. This way, the complete traversal of the tree is written. Now, you might have some doubt regarding the traversal for the second tree. This is your homework or this is your task that do the traversal for the tree too if you are new to it and figure out the part. Fine. The traversal way is the same as the previous tree one, so it will be easier for you. So, if you have any doubts or confusion about the solution we arrived at and how we arrived at it, I would suggest going back and understanding the intuition, then the approach, and then the code. After that, do a dry run by yourself on 2, 3 examples, and I'm pretty sure you will understand both the solution and the thought process behind it. So, now let's move to the next slide. Now, since we are familiar with the problem and the solution, let's move to the lead code and code the solution. Okay. The first thing is that declaring of the lists v1 and v2. Fine. Second thing is calling for the helper function named if fine. We will pass v1 and root 1. Second time also we will call pass v2 and root 2. And at the end what we will do, we will check if return v1 is similar to v2 or not. Fine. Now let's code the helper function. So this is the helper function. Let it be v, let it be root. Yes, and that's all. If not root, we return fine. Else we will check if root dot left is none and root dot right is also none. Fine. Then nothing there. Just append the value. Root append root dot val. Fine. Then we call for the leaf with self dot leaf v and root left. Self dot leaf v with root right. Okay. Now let's try running the test cases. Okay, the test cases have been successfully solved. Now let's finally submit it. Okay, we have successfully submitted our solution. Now the code of the problem is available in the GitHub repository. You can find the link in the description. Thank you everyone.